In free electron theory of metals, today we are going to discuss Hall effect in metals. Actually, this Hall effect in metals is a very important problem of free electron theory of metals. In fact, this Hall effect was invented by A.C. Hall in 1879. That is the theory which is called free electron theory of metals. This was proposed by Drude and Lawrence in 1900. So this phenomenon was invented before the free electron theory of metals. But after the advent of free electron theory of metals, this phenomenon was explained. So here our aim is to explain Hall effect in metals by using the free electron theory of metals. So first of all, we will know what is this Hall effect. For knowing this, let us consider that this, let us say A, B, C, D. Say this is a specimen of a metal, and an electric current is flowing in this x direction, okay, and this current is I, and if current is in x direction, the current density vector J will be also in this direction, okay, and here this conductor or this specimen of metal is placed in an external magnetic field which is probably very strong, and that external magnetic field B, or you can also say it H, has been applied perpendicular to the direction of flow of the current. I have shown here that this magnetic field B is in the direction of vector K, that is in Z direction. So you can say that magnetic field is in Z direction, okay. Then actually it is found that when this current carrying metal piece is placed in this external magnetic field, where magnetic field is perpendicular to the flowing current, then it is seen that the upper surface AB of this conductor gets positively charged and the lower surface gets negatively charged. In fact, what happens in this case, that due to the applied magnetic field, the drifting electron, when current will flow in positive x direction, the free electron of the metal will be drifted with a velocity, let us say Vd, in negative x direction, okay, because electron has negative charge, and that electron actually experiences this magnetic force which is given by this formula. This is minus E V cross B, okay, and due to this magnetic force, the electron experiences a deflecting force, and actually these electrons are deflected and deposited or accumulated on the lower surface. As the lower surface is negatively charged, and the electrons are shifted from the upper surface to the lower surface, so definitely the upper surface will get positive charge in equal amount. Actually this phenomenon which was observed by Hall in 1879, this is called actually Hall effect in the honor of his name. So I have mentioned it here. You can see when magnetic field is applied on a current carrying conductor in a direction perpendicular to the direction of flow of current, then there is a sideways deflection of charge carriers, and so that the electric field and hence the voltage is developed perpendicular to the current as well as the magnetic field. Actually, since the upper surface has been positively charged and the lower surface gets negative charge, so in this region or inside this metal, from the theory of electric field, that electric field will be produced in a direction from this upper surface to the lower surface, and this electric field is an internal electric field actually, okay. This is an internal electric field. because it has been produced due to the deposition of electric charge on the upper and the lower surface. Actually, this field in equilibrium state is called Hall field, and since you know where there will be an electric field, definitely there will be a potential difference or voltage. So this upper surface is at higher potential in this condition, and the lower surface will be at lower potential. Okay, so a potential difference is set up between the upper and lower surface, and that potential difference in equilibrium condition is called Hall voltage. So this development of Hall field and Hall effect, Hall field and Hall voltage just in a direction perpendicular to both the electric current and the applied magnetic field. This phenomenon is known as Hall effect. Okay, so I think you have understand what is this Hall effect. Now, actually our aim is to explain this phenomenon by using the concept of free electron theory of metals. Actually, for explaining it, I have shown it here, a specimen of metal in the form of a parallelopiped or a cuboid. Okay, and I have taken the three coordinate axes. You can see this is x-axis, this is y-axis, and this is your z-axis, which are along the sides of this cuboid. Okay, and we consider that between these faces, let us say the faces on which this x-axis is perpendicular, actually between those two faces we connect an external battery so that a potential difference is set up and an electric current gets constituted which flows in the direction of x-axis. As I have mentioned it here, this Ix, the subscript x has been used to show that this current is in the direction of x-axis. Okay, flows through this conductor. And you know, if the current will flow in x direction, then the free electron which constitutes this current, that will flow in the negative x direction. So this Vx represents the velocity of the drifting free electron, and its velocity is in the direction of negative x-axis. And you also know, if this phase is at higher potential and this phase is at lower potential, then current will flow in positive x direction. And so an electric field will be developed, which I have written here Ex, from the higher potential to the lower potential. So this Ex is the external electric field. Actually, this electric field has been applied by the observer. Okay. Now, in this condition, as electrons are drifting in negative x direction, and here this conductor is placed in a strong magnetic field, which I have shown here by this Hz, which acts in z direction. So this magnetic field is perpendicular to the current flowing in the conductor. Okay. So what will happen? Now you can see the electron is drifting with velocity Vx in this negative x direction, and current is flowing in the positive x direction. Okay, and a magnetic field Hz has been applied here on the conductor in positive z direction. So due to this magnetic field, the drifting electron will experience a magnetic force. What will be that magnetic force? What is its magnitude? What is its direction? And what will be its effect on the motion of the free electron? You cannot see. So I have mentioned it here. You can see, since magnetic field H has been applied in z direction, but in general you write H as Hxi plus Hyj plus Hzk. But since magnetic field is along the z direction, so its x and y component will be 0, and therefore you can say that H is simply equal to Hzk. Okay, And as you know, electron is drifting in negative x direction. Why? Because electron has negative charge, and you know the conventional direction of electric current is in just opposite direction of the flow of negative charge. Since current is in positive x direction, so the drift velocity of electron Vx will be in negative x direction. So V has only one component, that is x component, so I have written it here, V is equal to minus Vxi. Okay, and all the explanation which I have just told to you, I have mentioned it here. You can note down these things in your notebook. Okay, now we have to know what is the magnetic force acting on the drifting electron due to the magnetic field H. Okay, actually H is the intensity of magnetic field. In general, if you write the expression for the magnetic force in SI unit, you write the expression, this is Lorentz force actually, Fm equal to minus E times V cross B. I hope you have an idea of this formula. Here minus E is the charge of electron. So if you will write the equation in vector form, you must write the sign of the charge. Okay, and this expression has been written actually in SI unit. But if your aim is to write this equation in electromagnetic unit, you know, then Fm will be written as minus E over C times V cross H. Here C, you know, is the speed of light in free space. Okay. Now for getting the magnitude and direction both of this magnetic force acting on the electron, we will express this V and H in terms of its components in vector form. So you know this Fm will be equal to minus E by C, since V is equal to minus Vxi and H is equal to Hzk. Now you know I cross K, what is this? This is equal to minus J, you know, and this minus will make it plus, and so this minus sign will remain at each. So Fm will be equal to what? This is E Vx times Hz over C minus J. So what are you seeing here? This magnetic force is acting in negative zy direction. Okay, so the drifting electron here will experience a magnetic force Fm in negative y direction. It was moving in negative x direction, but it experiences a magnetic force due to the external magnetic field in negative y direction, as you can see it here. So what will happen? Actually in this condition, you know, since magnetic force is acting in negative y direction, but the velocity of the electron is in negative x direction, so the electron will follow a parabolic path, and this will get deflected and will get deposited at the lower surface. And so the electron, free electrons you can say, are depositing at the lower surface of the specimen. So I have mentioned it here. You can see it is clear that the drifting electrons experience magnetic force in negative y direction, and therefore the electrons are deflected and accumulated on the lower surface of the specimen, and thereby an equal amount of positive charge will appear on the upper surface, and this is actually Hall effect. Now as this is your upper surface, I have shown it here, these are positive charges, and at the lower surface negative charge has been appeared. But you know, due to this charge distribution, an electric field will now be created, and you know electric field is away from the positive charge and towards the negative charge. So an internal electric field, this electric field has been not applied by ourselves, this has been created due to the rearrangement of charge. So an internal electric field E will be created which will be directed in negative y direction. So I have written it here that this E is equal to minus Ey times J. Okay. But you also know that if in this region there is an electric field now which is directed from upper surface to lower surface, and you know, you have definitely studied in your course on electrostatics that electric field is always directed from higher potential to lower potential. So definitely this upper surface will be at higher potential and this will be at lower potential. So a potential difference will appear, or a setup between these two surfaces, okay, or a voltage will appear. So and this voltage is also an internal voltage. This has been created or produced due to the rearrangement of charge. Okay. So all these things I have mentioned it here. You can note down these things in your notebook. Now, you know, as now, apart from the electric field Ex, which is an external electric field, now in this region an internal electric field Ey has been also created, and you know, this electric field will also exert an electric force on the drifting electron. So apart from the magnetic force which acting on the electron, which was due to the external magnetic field, now our electron will also experience an electric force due to this internal electric field Ey. So what is this force, what is its direction, and what its effect will be on the electron? Now we will see. So let us see. You know, electric force acting on the electron due to the internal electric field Ey will be equal to what? This will be Fe equal to minus E times Ey minus J, because this Ey is directed in negative y direction. Okay, negative y direction. And so this will be simply Fe equal to Ey times J. Minus minus will become plus. So actually this electric force acts on the electron in positive y direction. And you have seen that the magnetic force is acting on the electron in negative y direction. So Fe is just anti-parallel to Fm. Our electron was deflected in downward direction due to the magnetic force, but this force is now opposed by the electric force acting on the electron due to the internal electric field developed inside the specimen. Okay. But as the deposition of charge increases on the lower surface, equally the positive charge also increases on the upper surface, and the strength of the electric field Ey get increased. Here magnetic field is constant, that is external magnetic field, but this internal electric field Ey is not constant. Its strength will increase with the increase in charge deposition. Okay. So now our electron is experiencing two forces. One force is electric force, which is due to the internal electric field. Okay. And another is the magnetic force, which is due to the external magnetic field. Okay. So the net force F acting on our electron will be the vector sum of these two forces. So you can write the resultant force acting on the electron F equal to Fe plus Fm. Now let us substitute the values of Fe and Fm. You know, Fe is equal to Ey times J. You can see equation number 2. And you have seen that Fm is equal to minus E times Vx times Hz divided by Cj. Okay. So now you can take this E and J as a common factor. So finally the resultant force is F equal to E times Ey minus Vx Hz divided by Cj. Okay. And if you want to find the magnitude of this force, this magnitude will be E times modulus of this much. This is Ey minus Vx Hz divided by C. Okay. But as I have told you that in this expression, this Ey is increasing. Okay, Ey is increasing. So a time will come when this Ey will have such a value that it will become equal to this Vx Hz divided by C. And what will happen when this Ey will increase to a value equal to Vx Hz by C? Then the resultant force on the electron will be 0. But never Ey will be greater than this much. Ey is never greater than Vx times Hz divided by C. Why? Because you know here this magnetic field is the cause of the production of electric field. So nothing can be exceed from its cause. So the value of Ey will never attain a particular value which will be such that the electric force will increase the magnetic force. Electric force will be never greater than magnetic force. Maximum its value will be equal to the magnetic force. And in that condition we say that equilibrium state has been achieved by the specimen. That is, the electric force now cancels the magnetic force. And in that condition, the further deposition of electric charge of electron on the lower surface is stopped, and the charge at the lower surface and at the upper surface becomes constant. Actually, the value of this Ey at that moment when this equilibrium is achieved, that is called Hall field. That maximum value of Ey at which equilibrium is established, that is electric force and magnetic force acting on the electron becomes equal in magnitude but opposite in direction. That value of internal electric field Ey is called what? That is called Hall field. And the voltage across the upper and lower surface of the specimen at that very moment is called Hall field. That is called Hall voltage. Okay. So now you can find what will be the value of Hall field and the Hall voltage. For getting the Hall voltage, we will think about the equilibrium condition when the net force becomes 0. And as F is 0, so you can say that this E times Ey minus 1 over C Vx times Hz is equal to 0, and so that this Ey is equal to Vx times Hz over C. Actually, this is the maximum value of internal electric field which is developed inside the specimen, and it is directed from upper surface to the lower surface. This maximum value of Ey is called Hall field. What is this? This is called Hall field. Okay. Now, if you consider that the thickness of our specimen between the upper surface and the lower surface is equal to d, which I have shown in this figure, then can you say what will be the potential difference between the upper and lower surface? You know, from the relation between voltage and the electric field, you know that voltage which will appear between the upper and lower surface in equilibrium condition, that voltage has been denoted by Vh, and that will be simply equal to Ey times t. And Ey, which has been defined in this equation 4, which is called Hall field, that is equal to Vx Hz over C. So Vh will be Vx times Hz into d over C. So this voltage defined in this equation 5, which is the maximum voltage appeared between the upper and lower surface of the specimen, that is called Hall voltage. Okay. So I think you have clearly understand what is this Hall field and what is this Hall voltage. Hall field is what? This is the maximum value of internal electric field developed between the upper and lower surface of the specimen directed from upper to lower surface in our present condition. Okay. And the voltage corresponding to this internal field is called Hall voltage. Okay. Now after getting the idea of Hall field and Hall voltage, now we are going to know about a very important quantity which is called Hall coefficient. So what is this Hall coefficient? We will now define it and we will find the expression for this Hall coefficient. As you have seen that we have assumed the electric current has been passed through this specimen in x direction, and we have assumed that this electric current is Ix, and corresponding to this electric current, the magnitude of the electric current density, we assume it is Jx. In fact, current density vector is always in the direction of current. So Jx is the current density vector and it is directed in x direction. And we also consider that this small n, this is the concentration of free electron in the specimen. When you say concentration of free electron, what does it mean? It means this is number of free electrons per unit volume. Okay. Then you have definitely studied the idea of drift velocity. I have used the idea of drift velocity in my previous lecture too, and you know, if Vx is the drift velocity, n is the number of free electron per unit volume, and minus E is the charge of an electron, then this Jx is given by minus Ne times Vx. This is a well-known formula, and from this you can find the value of drift velocity Vx, which will be minus Jx over Na. Okay. Now this value of Vx we will use in equation number 4. You can see this is your equation 4 where Hall field has been defined. Now the expression for Hall field will be written in terms of the value of Vx, which we have obtained here in terms of the current density. So let us substitute minus Jx over Ne at the place of Vx in that equation. Then you will get that Hall field Ey is equal to minus Jx over Nec times Hz. Okay. And so rearrange the term, Ey divided by Jx times Hz, that will be equal to 1 over Nec with this negative sign. Actually, this quantity is denoted by the symbol Rh, and this Rh is nothing, this is called Hall coefficient. This is also an important result. We will use it sometime later. So I have marked it by equation A. Okay. So now you can see this Rh, which is equal to minus 1 over Nec. This is called Hall coefficient. Okay, Hall coefficient. So Hall coefficient will be different for different metals, because you know this number density, that is concentration of free electron, will be different for different metals. So Hall coefficient is also different for different metals. But if you will write the expression for this Hall coefficient in SI unit, then this C will be omitted, and this Rh will be then equal to minus 1 over Na. So in SI unit, Rh is defined by minus 1 over Ne, but in electromagnetic unit it is written minus 1 over Nec. Okay. Actually, this minus sign in this equation indicates the charge, the sign of the charge carrier. Actually here we have considered that the charge carrier is electron, and electron has negative charge. due to that this minus sign appears here. If you will consider that our charge carrier is positively charged, let us consider holes are the charge carrier which has positive charge. In that condition, Hall coefficient will be positive, and we will write that RH will be equal to 1 over NEC. Okay, in electromagnetic unit, and in SI unit it will be simply RH will be equal to 1 over NE. That is, there will be no minus sign here. So you can say that this Hall coefficient, the sign of the Hall coefficient depends on the sign of the charge carrier. If the charge carrier is negatively charged, Hall coefficient will be negative, but if it is positively charged, Hall coefficient will be positive. Okay, I think you are getting the things. Now you have seen here, as I have mentioned, that I have marked this by equation A, that this RH is equal to actually EY divided by JX times HZ. So from this relation we can obtain a very important result. You can see EY divided by JX times HZ is equal to RH, and so the Hall field in terms of the Hall coefficient can be written as RH times JX into HZ. This is actually the value of Hall field in terms of the Hall coefficient RH. Okay, so in this way we have expressed the Hall field in terms of Hall coefficient RH. Okay, now we will define two very important quantities. One is mobility of this charge carrier and another is called Hall angle. So what is this mobility? What will be the expression for mobility of the charge carrier and the Hall angle? Now we will see it. I hope you have an idea of mobility of charge carrier. What is this mobility? You know, when EX field is applied, then our charge carrier moves with velocity Vx, which is drift velocity. So when unit field of unit strength will be applied, then what will be the drift velocity? That will be Vx divided by Ex. Actually, the drift velocity acquired by a charge carrier when an electric field of unit strength is applied, that is called mobility of the charge carrier. So if you denote the mobility of charge carrier by the symbol mu, then mu is defined by Vx over Ex. Have you got the idea? What is mobility? Mobility is the drift velocity of the charge carriers moving under the electric field of unit strength. So when electric field has a strength Ex, then drift velocity is Vx. So by unitary method you can say if the field strength is unity, then the drift velocity will be Vx by Ex. And so Vx by Ex is the mobility of our charge carrier. Okay. Again, you have seen earlier in the equation 4, I am not turning the page, but you can see we have obtained the value of Hall field in the first of all like this, EY equal to Vx times Hz divided by C. So now our aim is to express this Hall field in terms of the mobility of the charge carrier. So now from equation 10 you can see that Vx will be equal to what? That will be mu times Ex, mu times E, where mu is the mobility. So if your aim is to express now the Hall field Ey in terms of the mobility of the charge carrier, you can use this relation Vx equal to mu x in the expression for the Hall field Ey. So Ey will be now given by mu times Ex times Hz divided by C. So this is the expression for Hall field in terms of the mobility of the charge carrier. Okay, but we have earlier obtained the expression for this Ey, that is Hall field, in terms of the Hall coefficient RH. See this equation here. Hall field has been defined in terms of the Hall coefficient RH. So we have defined in equation 9 Hall field Ey. We have also defined Hall field Ey in this equation 11, but in equation 11 Hall field is in terms of mobility mu, and in equation 9 it is in terms of the Hall coefficient RH. But we have defined the same thing Ey in both cases. So you can equate these two equations. So equating these two equations, you will get that mu times Ex times Hz divided by C is equal to RH times Hjx times Hz. Okay, you can equate it. Now let us simplify this. From this result you can find the mobility mu in this way. This is C times RH Jx divided by Ex. Okay, because here this Hz and Hz will cancel out, and so mu will be this much. Okay, but you know, you have definitely an idea of vector form of Ohm's law, and I have discussed this vector form of Ohm's law in the Drude model of free electron theory of metals, that J is equal to sigma E. What is this? This is actually the vector form of Ohm's law, okay, or the microscopic form of Ohm's law. So when we will write this law for the x component of the vectors J and E, you can write that Jx is equal to sigma Ex. So according to microscopic form or vector form of Ohm's law, we can say that this Jx is equal to sigma Ex. And so Jx over sig Ex, this will be equal to sigma. And see this equation 12. In your equation 12, there is a factor Jx over Ex. You can see. So instead of Jx over Ex, now you can write sigma, which is electrical conductivity of the metals. So in terms of sigma, sigma is what? This is electrical conductivity. Conductivity. Electrical conductivity. Okay. So in terms of sigma, the expression for the mobility of the charge carrier is now this: mu equal to C into RH into sigma. Okay. Again, if you will write this equation in SI unit, you have to drop out this C, and mu will be simply equal to RH times sigma. Okay. Now let us see this equation number 11. Okay, where this Hall field has been defined in terms of the mobility. As you can see from this equation, if we will find the ratio of Ey and Ex, Ey, you know, this is Hall field, and Ex is the external electric field. Mark it. Both has different origin. So from that equation you can say that this Ey divided by Ex is equal to mu times Hz divided by C. Okay, but when you will use the expression for mu which you have obtained in this equation B, then you will get that this Ey divided by Ex is equal to this much. This is C times Rs sigma Hz divided by C. Okay, and so this C and C will cancel out, and actually this ratio Ey divided by Ex, that is equal to tan phi, where I have shown this angle phi. Okay, in fact if this is external electric field Ex, this is the internal field, that is Hall field Ey, and if E is the resultant of these two fields, then the angle made by the resultant electric field vector with the external electric field phi is called Hall angle. This angle is called Hall angle, and from the geometry of this figure you can see this tan phi will be equal to Ey divided by Ex. So tan phi is equal to RH times sigma times Hz, where phi is called Hall angle. But it is found from experiment that actually the value of this Hall angle phi is very small. And you know from calculus that if angle is very small, then tan theta is equal to simply theta, because you have studied in calculus that if theta tends to 0, tan theta over theta is equal to 1. So tan phi will be equal to phi in case of very small value of phi. And really, in reality, phi is very small. So instead of tan phi, we will now write simply phi. So Hall angle is given by RH times sigma times Hz. Okay. So these are the basic theory of Hall effect, and we have calculated the value of Hall field and Hall voltage in terms of mobility, in terms of electric conductivity, okay, and in terms of the Hall angle. Okay. Now finally, we are going to see the experimental determination of Hall coefficient, or you can also say that this is experimental verification of Hall effect. Okay. If a question will be asked that how this Hall effect is experimentally verified, and another question is how you can determine Hall coefficient experimentally, answer will be same, because if we will design an experiment where Hall effect will take place, and we will calculate any quantity which agrees with the standard value, then that supports the theory, that validates the theory. Okay. Now the experimental arrangement has been shown in this figure. I have considered here a specimen of a metal in the form of a cuboid or parallelopiped, and you can see that between this phase 1 and phase 2 an external battery has been connected, so that an electric current I will flow through this specimen from phase 1 to phase 2. Okay. And for measuring this current, a milliammeter has been connected here. Okay. And as you know, when this specimen will be placed in a strong external magnetic field perpendicular to the electric current, then Hall effect takes place. So I have shown here that a constant magnetic field Hz, which is perpendicular to the current flowing in this conductor, has been applied. Then you know Hall effect will take place. The upper surface will get positive charge and the lower surface will get negative charge, because in metal the charge carriers are free electrons according to the free electron theory of metals. Okay. And so a Hall voltage will be developed between this upper surface 3 and the lower surface 4. To measure the Hall voltage appeared between the upper and lower surface, you can see here a potentiometer is connected which measures the Hall voltage. Okay. And for calculation, we have assumed that the length of this specimen in the direction of flow of current is L, its breadth is B, and its thickness is D. Okay, I have assumed. Now, when the current will flow, magnetic field will be applied, Hall effect will take place, and we can measure the current flowing in the through the conductor by this milliammeter. And what voltage appears between the upper and lower surface, that will be read, that will be noted, that will be measured by this potentiometer. So measuring the Hall voltage, now you can see we can easily measure the Hall coefficient. But how? See the calculation. As I have shown here, that L I have assumed is the length of the specimen, B is its breadth, D is its thickness, and I is the electric current flowing through it. Actually, for the accurate measurement, there is a necessity of the experiment, there is a demand of experiment that the breadth and the thickness of the specimen must be much smaller than its length. So, for accuracy in measurement, you have to take a specimen such that B is much smaller than L and D is also much smaller than L. Now, what will be the current density? You know, current density is simply current divided by area of cross section, and as you can see, this current enters through this phase 1, okay, and it leaves the specimen through this phase 2. And what is the area of cross section this phase 1? This will be simply B times D. So at the place of area, I have written B into D. So Jx is I divided by Bt. Okay. Now you have learnt just now that the whole field Ey is given by Rh times Jx times Hz. Okay. But Jx, you have seen this is I divided by Bd. So Ey will be equal to Rhi Hz divided by Bd. Now let us multiply this Ey by D by taking the cross multiplication. So Ey times D will be equal to this much. This is Rh times I divided by Hz divided by B. Okay. But what is this Ey into D? You know, Ey is the whole field and D is the thickness of our specimen, that is, this is distance between the upper and lower surface. So Ey into D is the whole voltage. So whole voltage is equal to Rh times I times Hz by B. And so Rh is equal to B times Vh divided by I into Hz. Okay. Now you can see, if your aim is to measure this Rh from this experiment, for that all quantities in RHS of this equation must be measured from the experiment. Here B is the width of the specimen, which can be easily measured by the scale. I is the electric current flowing in this specimen, which is measured by this milliammeter. Okay. And Hz, this is the strong magnetic field. We actually apply the known magnetic field, so Hz is already known. And if your aim is to measure the strength of this Hz, you can measure it by another meter. And Vh is the hall voltage, and we have connected this potentiometer to measure the hall voltage. Directly this potentiometer gives the reading of hall voltage. So in this way, measuring all the quantities in RHS of this equation, we can easily measure the value of RH, that is the Hall coefficient. Okay. And if your aim is to just verify this Hall effect, then you have to say, since a Hall voltage appears, so this verifies the Hall effect. The appearance, the production of this Hall voltage is the proof of the Hall effect. So this is also an experimental test for the Hall effect. Now basically we will see that there are three important applications of this Hall effect. First one is determination of sign of charge carriers. As you have seen, by knowing the sign of Hall coefficient, we can decide what will be the sign of the charge carrier. If Hall coefficient is negative, definitely the specimen has negatively charged carrier. Okay. And if Hall coefficient is positive, the charge carrier will be of positive charge. Okay. So knowing the sign of Hall coefficient, we can decide the sign of charge carriers. This is one of the most important applications of Hall effect. Again, you can see in our calculation this N, which is called number of free electron per unit volume. Actually, this concentration of free electron can be also measured by the use of this theory. Okay. And now see this last expression here. If you know RH already, you know VH, you know I, you know B, then from this equation A, you can measure the magnetic field. So if magnetic field is unknown, but Hall coefficient and Hall voltage are known, then Using the same expression, we will be able to measure the magnetic field. So this Hall effect is also used to measure the strong magnetic field. Okay, so this were all about the Hall effect. I think this was a very interesting session, and definitely you have understand each and every aspect. And remember, this Hall effect is very important for your examination purpose for any type of examination which you face. Okay, thank you very much.